Okay, it's been a while since I've done a what is a tensor lecture, and it is time to get back to it. And where we left off was with this notion of constructing a model of space-time where we had a coordinate system and we established all of the points, P, Q, R, I guess T, on space-time, and we understood that at each point we were going to affix a vector field or a vector space, which would immediately come with its covector space and all of the tensor product spaces. Each one would be a four-dimensional vector space, real vector space, and we do this at every point in space-time. And I kind of went on and on about it during the very last What is a Tensor lecture. And the problem is I kind of realized that this is a very hand-wavy argument, because what I'm really talking about, of course, well, not of course, but what I'm talking about is a fiber bundle, more specifically a tangent bundle, well, among other types of bundles, but this is a fiber bundle. That's what when you take the total universe of all of this together, all of these points on space-time and all of the vector spaces attached to them, you really have a fiber bundle concept going on. And also, the underlying space-time itself, I kind of realized, well, that's really a manifold. And what I realized wasn't these facts. I mean, I always knew these facts, but I realized I was trying to get by without describing the details of what this is and the details of what that is. And in a way we can do it, but that's when I got diverted to the What is a Manifold series of lectures, where I covered all of this. Oops. And it turns out there's more of these lectures than there are of the What is a Tensor lectures. Well, it's important, right? If you really want to get into this subject, if you really want to know what's going on, there's no evading it. You have to learn about manifolds and about fiber bundles, and if you really want to understand those, you really got to know topology. Everything is couched, and when they define these concepts, when they define a manifold, when you define a fiber bundle, you're couching every element of that description involves open sets and mappings and differentiable functions on manifolds. And the language of all of that is the core alphabet is topological topological spaces and topology. So anyway, I do recommend you give that a go and you stick with it and nail that all down. As it is, we still can proceed, and I ultimately think that we'll be fine without having to necessarily go through that whole diversion. But I urge you to consider it. I hope from time to time I don't slip into the language about a manifold. The big point is the notion that this blank slate here, this blank mess, this undescribed something, well, that's what reality is. Reality is space-time. Reality is it is what it is. It's our empty space. It's where things happen. But on the top of that space-time, we're bold enough to lay down a coordinate system. And if we're going to do that, there's rules for this. You can't just lay down a coordinate system on any type of mathematical object. You have to do it very, very carefully. And all of that care, all of that formal, delicate attention is all done through the subject of differentiable manifolds. And that tells us also, how to change coordinate systems, right? If we want to do a different coordinate system on this manifold. The very fact that I'm drawing it this way, as opposed to, say, something like this, where the coordinate system is more of a polar nature. The fact that all of these things are compatible on a space-time is entirely dependent on that other subject. So, but where we left last time is after, and we just can't get away from this picture, so I keep drawing it, is that everywhere where we've established these vector spaces, and I'll just symbolize the whole damn thing with a V, but everywhere where we have this massive amount of we call each one of these a tangent space, right? And in each tangent space, and the tangent space would be TP if this is the point P, and the tangent space here will be TQ. And the tangent space is a vector space, and there are separate vector spaces for each place in space-time. So from the tangent space, we knew that we could create a vector. Any vector in that tangent space will have this contravariant component with this covariant basis vector. And we now understood that we're talking about vector fields. So we're talking about this contravariant component object as being a function of space-time. And we don't have to show that this is a function of space-time, but we have to understand that it's evaluated at the point x, right? And that's how these basis vectors change throughout space-time, is where they're evaluated. And likewise, we can do the covariant, or we can do the cotensors, which have covariant indices and contravariant basis vectors. And again, they are also functions of space-time. But ultimately, we now know that whenever we talk about a vector, we're really talking about a vector field. Very, very rarely in this subject do we actually ever zero in on one point and the vector space at one point. We talk about the entire vector field. So we always talk about it as a function of space-time. But because of that, we tend to suppress this because it gets really cluttered. And every time we see this expression, we now understand it to be this expression, right? And that's going to be true of tensors also, right? If I have a tensor t, well, let's not use t. If I have a tensor q, alpha, beta, delta, we know that it's going to be a function of space-time, and we know that we're dealing with this tensor product, dx delta, like that, and this is now a tensor field because at every point in space-time, this thing here defines the component value of this particular component, whatever the alpha, beta, and deltas are assigned to be. And that is how we put a tensor field onto space-time. And whenever we see this, we know that there's an applied function of space-time. It's just how we're going to do it. Now, and again, in general relativity books, in typical general relativity textbooks, as I think I've said several times, they kind of leave this out, and they leave index gymnastics to keep everything straight. So if I just saw this alone, I would still think of it as a function of space-time, and implied are all of these basis vectors that are hanging out. We know exactly what basis vectors are here, because we just look at the indices, and we immediately just make the Einstein sums work, right? Down alpha, down beta, and up delta, right? And that's so we can do this automatically, right? And out of extreme efficiency, general relativity books don't throw that in. And I've been doing it constantly, putting it in there in this lecture. All right, so and then we also learned, if I recall correctly, it's funny, it's because I'm recalling stuff that I've actually done, but it has been a while. That's true. But the transformations, right? The transformation properties of these things. That's another thing that we went through really quickly that I'll quickly scan again right now. So let's lay down just one other piece of, well, there's always one other piece of notation, right? But when we have our space-time, and I'll just call this the x1 and the x2 coordinate, but we know that there's an x0 and there's an x3 floating out there, right? And I've talked about how we created this this vector field, for example, x alpha partial alpha, and sure enough, yeah, they exist at each point, and we have a field, so we know we have it existing everywhere. But I want to talk about all of them at one time. I want to talk about all of these, all the architecture that we've put in on our space-time all at once. Well, in particular, the vector spaces I put at every point all at once. So we know that the language for a single point was TP as the vector space at a single point P. But it's very common to see this, TX M, where the space-time itself is given the script letter M or some letter M. I'm going to use script to be distinguish it from other uses of the capital letter M. But M was sort of usually would stand for something like the manifold, which I briefly touched on. But this is the manifold of space-time. We call that M. If I put this M next to the TX, I'm actually now talking about the complete collection of all of these vector spaces at every point all together. And because of that, it is the grand tangent space of the entire manifold, right? Because it's now this whole thing thought of as one integrated whole. And if I go to each point X and I pull out a single vector, right? If I pull out a single vector at each point X, that's what a vector field is, right? A vector field is a single vector drawn from the local vector space at every point. And if I did that across the whole manifold, that collection of single vectors being a vector field that I might, if I was being completely detailed, which I might write like this, that single vector field is an element of this object. It's an element of the total tangent space. And because of this, what we say is that vector fields we say they're elements of this total tangent space. And when I talk about the tangent space of the spacetime or of the manifold, or just the tangent space, I really am going to be meaning this thing. I'm never going to talk about the tangent space of a point very often, but when I talk about the tangent space, I'm now talking about this total collection of all tangent spaces. And when I talk about an element of the tangent space, I'm now going to mean an entire vector field. And the reason that's important is eventually, very soon now, in fact, our next lecture, we're going to talk about something called the connection, which is a map from this collection of, the set of all vector fields, which is really, I guess that's the set of all vector fields, right, to to some other place, and I don't want to get into it now. But that range space is a tensor product of things that look like this. So in fact, it's just it's the set of all tensor fields, tensor product with the set of all. Let's see, I think it's covector fields here is the way to do it. So we'll get into that. We'll get into that next time, though. But I want to make sure we understand when we talk about tangent spaces now, we mean the whole darn thing. Now, the other thing to keep in mind now is what happens to our domain space when we talk about vector fields and covector fields. Right? We know that if you have a single vector v and a covector w, I guess what was our notation for that? Nope, that's not how I did it, right? That's sort of the complex notation of the Dirac system, but a map, so how did this work? This was, let me get this down right. It's a map omega with a vector v, right? We knew that was a real number. Now, that's a single vector from the vector space and or a single dual vector from the dual vector space and a single vector from the vector space, which would be, say, T, P dual and T, P, and we would get that real number. But now we're dealing with something different. Now we're dealing with a whole vector field, right? So if I put a vector field in there and, well, I should say a covector field, right, in that first slot. If I put a covector field, let's see, how do I want to do that? Say it's lambda, covector field lambda, and then a vector field x. Now these are fields, right? So they're functions of space-time. The components are all functions of space-time. So in the end, it's not going to give me a real number. it's going to give me a real number at every point in space-time, because I do this point-wise. Right? I go to a point in space-time x, and I find out what that field's value is. And then I go to the same point in space-time x, and I find out what that field's value is. I find out what the vector field's value is. I find out what the covector field's value is. And then I take that inner product, or not inner product, I'm sorry, that dual space mapping, and I get a real number, right? I get a real number at that point in space-time. But I do this for every single point in space-time. So in reality, you've got to think of it now like this. Is an element of C, I'll call it infinity x. It's an element of the continuous functions, because it's almost always going to be continuous and smooth function, but it's an element of the functions on the space-time, because this will ultimately be a function of the space-time where this function takes space-time points and returns real numbers. So now you have to think of the dual space mapping as accepting fields and returning functions, real numbered valued functions on space-time, instead of thinking of it as a dual space covector, a vector space vector giving you back a real number. It's now a dual space covector field acting on a vector space vector field, tangent space vector field, and it returns a function on the space-time, a real valued function on the space-time. Very important point to understand, because now, from now on, this is what we're going to mean when we talk about a dual space mapping. Likewise with an inner product, by the way. So an inner product, which we used for, which we had a different symbol for, that inner product symbol was vector v with a vector w, right, where those were two elements of the tangent space at a point P. Well, that's now going to be a vector field and another vector field where they're members of the tangent space on the manifold, right? They're vector fields. Vector fields are elements of this tangent space on the manifold, and this would have been an element of the real numbers. This is now going to be an element of the continuous functions on the space-time, right? This is going to be, maybe I should write equals some function on the space-time now. And that's because, again, you're doing this process pointwise. Okay, so now a quick thing about coordinate transformations. So we knew that, for example, let's stick with our Q alpha, beta, delta, partial alpha, partial beta, and then the differential form associated with delta. We want to transform this because what we're doing is we're transforming the underlying coordinate system. When we transform the underlying coordinate system, it really drives changes in how these things operate because they're now operating along different coordinate lines, right? So that's one thing that's got to be accommodated. And of course, the components are going to change in this new coordinate system. And what do we remember about how to do that? Well, we know that, we know that partial alpha, which really means partial by x of alpha, right? In order to transform that with the x alpha in the denominator, we need dx, so we have our coordinate system. So we have dx alpha prime, right? That would be the covariant, right? The covariant transformation. And likewise, if we did dx, delta, which is what it is, in order to get that, so this actually, dx alpha, it transforms that way, right? Transforms this way. This transforms as dx delta partial x delta prime partial x delta, right? Which is, of course, the contravariant form of the transformation. So, and then for q, alpha, beta, delta, you'll see that it goes exactly the opposite. We'll need dx alpha prime, dx alpha to transform the first index, dx beta prime, dx beta to transform the second index, then dx delta, dx delta prime to transform the last index. So we kind of went through how these transformations worked also. And then you can see if we put all this together, everything cancels, right? You know, this guy here, this guy here, this alpha alpha prime is going to cancel with that. And this guy here, delta delta prime, is going to cancel with that. And the beta beta prime would cancel with the equivalent one of this for beta. And of course, because it's the same tensor, right? If you threw in every transformation everywhere, you would quickly see that they would all cancel because it should give you, I mean, ultimately something that is the same fundamental object. What happens is I use these to change the indices on this. So this ultimately equals q alpha prime, beta prime, delta prime, and I can replace this with this. I can replace the old coordinates with the new, and then these also get replaced with primes. So so that's how the coordinate transformations are done. Okay, so then so now we can actually think a little bit about a special rank 2 tensor. We can talk about g mu nu dx mu dx nu. And of course, I just feel the need to say this over and over again, but this is a function of space-time, right? And this guy is what we're going to spend a few minutes talking about right now. Now, you may remember that at each of these tangent spaces, at every point in space-time, I talked about them as purely vector spaces. But what is important is we want them to be inner product spaces, right? We want to give them an inner product. You remember we defined the inner product of a little vector v and a little vector w using this notation, where we put it in these brackets, these angle brackets. And this should be an element of the real numbers, right? When you execute this inner product on two vectors. And we also knew that once you had an inner product, you could create this thing, something like this, where you leave one of the slots blank, and what you've done there is you've actually created an element of the dual space, right? And it was an element of the dual space because it's waiting to eat a vector and turn it into a real number. Something that's waiting to eat a vector and turn it into a real number is a map from the vector space to the real numbers. And that mapping, this set, the dual space contains every one of those mappings. So this has to be inside the dual space. So therefore, once we had this inner product, the point is we created a correspondence, a natural correspondence between V and V star. It's natural in the sense that if you have an inner product, then this correspondence is suddenly established for free, right? There's only one correspondence like that, and that only exists if you have endowed an inner product with the vector space. We kind of talked about that a lot early on in the lectures of what is a tensor. So the problem is that we've set up this vector space at every point in space-time, but we haven't set up an inner product at every point in space-time. We don't have an inner product, so we still don't have a correspondence between the vector fields and the covector fields. We don't have a problem between a connection between all of the tensor product spaces, at every point. We can't correlate them with the I'm sorry, not the tensor product spaces, the tangent spaces at every point, we can't really correlate that with the cotangent spaces at any point because we don't have an inner product. So we're going to, and certainly if we had an inner product, it doesn't do us any good to have an inner product for that point only and not this point, right? So what are we going to do about that? Well, the answer is we are going to establish one big tensor field, G mu nu, and dx mu dx nu. Now notice in this case, I skipped the little tensor product thing here. So that's very frequently done, but it's always implied to be there if you don't see it. It's still supposed to be there. So sometimes from time to time I'll leave that out, but that's just because it's efficiency. We all understand what this is supposed to be, right? And likewise, we're supposed to understand that this is a function of space-time. And as such, well, what have we got? If we have this as a function of space-time, what are we saying? We're saying that we can establish a member of the rank 0, 2 tensor product space. At every single point in space-time, we are picking out one of these guys. We have basically a rank 0, 2 tensor field. We have a 0, 2 tensor field. We're gonna just say it's this. This is our favorite 0, 2 tensor field. We love this thing. Whatever it is that we love, we're going to call it G mu nu. And therefore, G mu nu is going to be a bunch of numbers, right? You give me a point in space-time, and I will give you, and remember, this point in space-time is x0, x1, x2, and x3, and I will give you a real number, right? A real number will be pumped out of this, and that real number will be relevant for that particular point. So I could, maybe it'd be G mu nu of the point P. Actually, the way I should write this is not of the point P, but I should use the coordinate function x, say delta of P, right? So, yeah, understand how that works. I'm tempted to write G mu nu of P, right? But P is really an element of the space-time. The question is, what are the coordinates of P? So the way to write that formally would be G mu nu times x delta of P. And that should give you x0 of P, x1 of P, x2 of P, and x3 of P. And these things are the coordinate functions, and we went on and on about them in the What is a Manifold lecture. So I can't help but pointing out, this is a little bit informal, and that's fine. The point is that every point in space-time will have a value, G mu, let's call it T, P, R, G mu nu T, G mu nu P, G mu nu of R. And the value, this value, this value, this value are all calculated through the function that we get for the entire field. And if we can lay down an entire field like this, or in the technical term, a section of the 0, 2 tensor field bundle that we're dealing with, then all of a sudden we have a metric tensor at every single point in space-time. And once we have that, then we now have the correspondence at every point between the tangent space and the cotangent space. And we have an inner product at every point in space-time. And that is what we're after, right? That's the gold here. Because ultimately, we've got this model of space-time, right? We've got these coordinate lines sort of organizing our space-time in some way. And we have no way of comparing vectors and covectors and tensors. We have no way of comparing them at any point, much less at different points. So in order to make those comparisons, we've got to know something like G mu nu. We've got to have this second rank, or this 0, 2 tensor field. We've got to have that. If we don't have that, we're lost because we can't compare these things. And we can't start studying things. We can't do physics without this thing. So the question is how do we pick G mu nu so that our model of space-time is a model of the real world, is a model of physics, right? You know, if I want to say there's a little piece of mass sitting here in space-time, you know, and how do, what do I want to know how that, and then there's another mass, and this mass is going to start moving. How do I know, is it going to be attracted and move around it? Why? Maybe it just moves straight. Maybe it moves away. I mean, I don't know. I've got to figure that out. That's what physicists do. We observe things, and we then write equations and make models. In order to figure that out, I have to have a very robust model of space-time and how it is structured and what it is, and maybe models of the forces between things. The model of the forces between things, that's a different branch of physics. The branch of physics we care about talks just about how space-time works. And the core element, the thing that actually defines the space-time, is this guy right here. In fact, if I ever say, hey, I have a Schwarzschild space-time, or I have a Kerr space-time, what that means is I have a metric that solves the Einstein's equations in certain circumstances. And this metric, I can call this, sometimes I can call this a space-time. This is a rank 0,2 tensor field. Great. But there's a lot of rank 0,2 tensor fields out there. Only one of them is the metric tensor field. Only one of them. And that's the one I care about the most by far. And also, it's so important I don't even call it a metric tensor field sometimes. Sometimes I just call it is the space-time. If I want to talk about the space-time, I just talk about this thing. And it's got everything in it. The coordinates are built in it, right, through these guys. The coordinates that are on the space-time are established in it. And it tells me how to measure everything in the space-time, how to measure these tangent vectors, how to correlate tangent vectors with cotangent vectors, and everything. So that is the goal here. The goal is to figure out what this thing is. And the way that's figured out is through the Einstein equation. And ultimately, we're going to get there and get at that. So I want to emphasize that's kind of where we're headed now. We understand how space-time works. We understand all of these vectors and tensor fields. We've answered the question, what is a tensor? That question is over. Now it's a lot of applied stuff to really get to the meat of what is a tensor good for, right? How does a tensor do physics for us? And so we're going to deepen our knowledge of tensors and explain what they do for the next foreseeable future with these lectures.